So we need to talk about intramolecular forces.
We just spelled Mars, M-A-R-Z-E, in your astronomy.
I know. I know exactly who it was, don't worry. So intramolecular forces. So what does intramolecular mean?
Inside the molecular.
Yes, inside the forces. Yes, inside the molecules, okay? Inside the molecule. So intra means inside, inter means between, right? So forces that exist between the atoms in a molecule. Yes. So intramolecular forces are forces that exist between the atoms in a molecule. Okay. So the potential energy of so with these forces, let's talk about this before we get into the potential energy of them. So we've been talking about bonds, right? About types of bonds. And what were the two types of bonds that we discussed? Covalent and ionic, right. So covalent bonds are bonds between things that have similar electronegativity. Ionic bonds are when the electronegativity is different between the atoms, right? So we're going to talk specifically about ionic bonds with intramolecular forces, okay? We'll talk about both of them, but, okay, so really what we're talking about here is like bond strength. Okay, so the strength of the bonds between the atoms, all right? Strength of the bonds between the atoms, and this is related to how much energy can be released when you break those bonds, okay? So bond strength is related, so example of an intramolecular force, example, really what we're going to be discussing today is bond strength. Okay. And bond strength, I don't think that I need to define that for you, but it is connected to energy released when the bond is broken. Okay. Okay. So, for instance, if we have a high energy bond, okay, so we'll make a graph here. Okay, so on this side, we're going to do bond strength. We're just going to abbreviate it as BS. Okay, BS, and this is going to be the energy potential. The energy of breaking that bond. Okay. This is that related to the electronegativity. It can be when we're talking about ionic bonds, yeah. And we'll talk about that. Okay, so it's probably it is a relationship. It is a positive relationship. Okay. So the y-axis is energy potential when it is broken.
So it doesn't directly release energy when broken. It just has potential.
Yeah. So, but when you break the bonds, it will release energy. But when it's in the bond, it is potential. It's a chemical potential energy. Okay. So we'll talk about both types of bonds. And again, this is not like an exact thing. I just wanted to show the relationship, right? So in a covalent bond. So let's talk about covalent bonds.
Hey, question. When are we going to talk about the reactivity series? I remember that from last year.
Reactivity series?
Yeah, where like aluminum can replace this element in the bond if you mix it in, but then it can't go the opposite way. Even though they both fit perfectly in there, one of them will, like if it attaches, it releases more energy than the other one has the bond strength, you know? Like,
Yeah, I know what you're saying. Reactivity series, I would guess it's probably Unit 5, which is about reactions.
I think it's like,
I have a couple of questions about our last reading.
You have some questions about the last reading?
Yeah. So when I was talking about like electron configurations, I was wondering why can the d orbitals have 10 electrons and the p orbitals 6, while the s 1 and 2? And why is there exactly four electrons between them?
As you go up the energy what is it, sublevels, and so you go to like D, so S and P and D, the more space there is to inhabit in the electron cloud.
But like, so 3D is higher, I'm sorry, you said 4D is higher than 3P. Wait, no, 3D is higher than 4S, right?
Higher in what?
In like energy.
Well, no, well, kinda, yeah. It's so. What is the question?
So like, why can the 3D hold 10 while then the 4S, which is like behind it, can only hold 2?
So that is where the electrons hang out. So we can look at models of what each sublevel represents in terms of where the electrons go. It's not a sphere around the atom. They are in electron clouds are shaped in different ways. Oftentimes they're like conical. And so there's more space in the D sublevel. There's more volume area in the D sublevel than there is in any of the S sublevels.
Oh. Okay, that makes sense. So like the S, P, and D describe also how they're shaped on top of probably.
Yes, yes. It shows the shape of the electron cloud, like where those electrons hang out relative to the rest of the atom. Okay, so in a covalent bond, the energy with the it's connected to the bond length, right? So So the bond length is influenced by the size of the atom's core, and it's related to Coulomb's law. All of this stuff is related to Coulomb's law, okay? So, and it is also related to, in covalent bonds, the intramolecular forces. That's not how you spell forces. Forces are related to the size of the atom and whether or not it's a double or a single or a triple covalent bond. Okay, and the order of the bond, which is single or double. Okay. So bonds with a higher order. So if it's a double, it has a shorter. It's a shorter bond. So the atoms are actually closer together, and thus the energy is higher. Does that make sense? The bond energy is higher. Because they're interacting more, right? And that is related to Coulomb's law. So Coulomb's law is not only applicable to atoms, but also the forces between atoms. We see how that works?
So a single bond would have less energy than a double bond?
Yes, a single bond has less energy and is easier to break than a double bond. And so remember, what a single covalent bond means that they are sharing one electron. One electron is going back and forth between the two atoms. A double is 2 electrons going back and forth, and a triple is 3 electrons going back and forth. Do we see how that works? Yeah? Ionic bonds are stronger than covalent bonds. Uh-huh.
Well, they have covalent bonds form such strong structures like diamonds and carbon fiber.
Do I have that backwards?
I'm pretty sure covalent bonds are stronger because ionic bonds are easy to break. You can just blow it solid.
Yeah, but
Ionic bonds are brittle.
okay, let's look it up. Okay, yeah, we get it. Just answer the question. Oh, the computer. Oh, the computer is struggling. Oh my goodness. I can't handle it. Oh no. Everything is going very poorly right now. Okay, let's see here. Electronegativity, blah, blah, blah. Just answer the question, man. Chemistry would study the interactions between atoms. So it says that covalent and ionic, including Linus Pauling's electronegative elements, which bonds are the strongest, it depends on their properties. So I guess there's no real rule of ionic and covalent are stronger. One is stronger than the other.
So credit that works is that ionics are, let's see, covalent bonds tend to be stronger. Or wait.
I guess the reason why we're confused about this is because it's a complex answer. It's not one is stronger than the other. It varies. Because my guess is that something like sodium sodium fluoride would be really strong. Sodium chloride, salt is also. No, because no. Because the intermolecular chipping away at salt, you're breaking the bonds between the molecules.
Yeah.
You're not breaking the bonds between the atoms.
Okay. So that's what you, no,
So
I thought that's what we were talking about.
yeah. So we're talking about bonds between atoms in molecules. And there can be ionic interaction between molecules, they're polar molecules, right? That's what hydrogen bonding is in water, surface tension. But yeah, you're right, that is much weaker, the interaction between polar molecules. But the bonds between, the bond between fluorine and sodium, or the chlorine and sodium, is super, super strong. Yeah, that's a good question. So yeah, this is intramolecular. Okay, not intermolecular. That can be confusing. Okay, so double, single bonds. So we better write that down. So what was it? It was double and triple bonds are shorter. Double and triple covalent bonds are shorter and thus stronger than single. Okay. The relationship that shorter the bond, the stronger the energy due to Coulomb's law, right? Coulomb's law. Closer together, you decrease the distance. Remember, you decrease the distance, you get stronger. If you increase the distance by 2 times, you decrease the energy by 4 times, because it's an inverse square law. Okay? It's an inverse square law. Yeah. Because remember, it was the charges of the 2 divided by the distance squared. Right?
It's a square root bond.
Square, not a square root bond. It's an inverse relationship squared. Yeah, so direct relationships are, you increase one number, the other number goes up. Inverse, increase one number, the other number goes down.
Can I like have an example?
Yeah. So if we just do this in math, x 2, whoa, what in the heck? 2x equals y. That is a direct relationship, right? X goes up, y goes up. Does that make sense? If you do x equals 2 over y, or you switch them. If y goes up, that means x goes down. Does that make sense? So this is a direct relationship. This is an inverse relationship. An inverse law is x equals 2 over y squared. That's an inverse.
2y to the power.
Yeah, you can do that too. But usually when you see a law like this, like Coulomb's law or Newton's law of universal gravitation, it's one number is squared underneath some other numbers. Okay, so that's, yeah, this is a direct relationship, and you could do a squared direct relationship, and this is, or you could do, or a direct squared law, and this is an inverse squared law. Does that make sense? So Coulomb's law is an example of an inverse square law.
What's the funny symbol again?
The what symbol?
The Coulomb's law symbol. It's like the constant.
Oh, isn't it just like H? Pretty sure it's just H. No, are you talking about the lambda wavelength?
Can you just write Coulomb's law?
Yeah, so Coulomb's law.
Yeah, like the charge 1, charge 2, what atom.
Let me just, instead of me writing this out, I'm just going to pull up an image of it because
C1, C2 over D.
it's D, yeah, it's D squared. But I'm pretty sure that the constant is just H.
Like a lowercase h.
Yeah. Oh my gosh. My.
H has too many tabs. We should just give it a Greek name.
Okay, it's not H. Sorry, it's K. Sorry.
Okay.
It's K. Yeah. K, Q, Q, D. Yeah. Okay. Moving on. So now that's in a
What is K?
it's Coulomb's constant.
No, I mean like
In numbers.
in numbers.
It's some.
Oh, it's 8.99 times 10 to the 9th.
Yeah. 8 to the 9th. Yeah.
So it's like 9.
Kind of. Yeah. It's very simple. Very close. Very close. Okay. So we can also use Coulomb's law to understand the strength of ionic bonds. Okay. So why can we use Coulomb's law to understand the strength of ionic bonds?
Because the energy in
Oh, you're so close.
That's the strength.
So what is Coulomb's law again?
It's
Force equals Coulomb's law, which is K, times Q1 times Q2 divided by distance squared. Right?
Yeah, where Q1 and Q2 are particles.
Where Q1 and Q2 are not particles, they are the what of those particles?
Energies. Positive and negative energy.
Oh, positive, yeah. Positive, negative. No. Come on, guys, you're so close. The energy, so Q1 and Q2 in Coulomb's law, you're so close.
Well, if we had the unit, then we could figure it out. What's the unit for these?
For the charges?
Oh, I know what the Q's stand for.
What is
Charges.
it?
so the Q1 is the sign.
It is the quantity of charge on object 1 in Coulomb's law. What that means, really, in Coulomb's, if you apply Coulomb's law to ionic bonds, it is the electronegativity. Okay, so it's related to the electronegativity, right? Because it is okay. So for instance, if you, yeah, it's the charge, okay? So ionic bonds, Coulomb's law, relates to the strength of ionic bonds, because the charges of the atoms are, oh, I need to make this wider. Charges of the atoms are the, like, it's like the electronegativity, right? So for instance, fluorine in a bond, fluorine is really negative, right? It's super electronegative, so it pulls the electron over to its side, so it becomes ionized very strongly, right? Has a very strong ionic charge, and whatever it's bonded to gets a very strong positive charge, right? And so you take the signs of those charges and you multiply them together, and the higher those numbers are, the stronger the interaction between the atoms, right? It's like in gravity, in the law of universal gravitation. If you increase the masses of both objects, your gravity goes way up, right? Does that make sense? Okay. Because the charges of the atoms are in an ionic bond, or what's the word I'm looking for? Like, it's created. It's the charges of the atoms are created by the bond. Okay. Do you get what I'm saying there? If you don't, let's talk about an example. Okay. So let's use chlorine this time. Okay. So we have chlorine. And there's pen, but they're really thin, so you can't see them very well. So let's say that chlorine bonds with potassium, okay? Potassium is much larger, right? Because of atomic radius, right? We've learned this. So where is my dipole going to be? Where is the negative charge going to be on our on this molecule? Toward chlorine, right? We're going to have the negative charge here. We're going to have the positive charge here. Chlorine has become K plus. And did I say chlorine? I meant potassium. Potassium has become K plus. Chlorine has become K minus, or Cl minus, right? And if we can look at the electronegativity of these two and compare them, and that will dictate the amount of that these have become ionized. Okay, really Cl minus, right, and K plus. The chlorine has stolen the electron, right? So they've become ionized. And so the higher the electronegativity difference between the two, the more that these become ionized and the stronger the bond is between them. Does that make sense for everyone?
Yeah, but how do we know that it's in the right proportion to plug that into this again?
And plug back into the what?
So we find the electronegativity of each atom by plugging it into Coulomb's law. And then you use the electronegativity in Coulomb's law.
No, you don't need Coulomb's law to find the electronegativity. The electronegativity would, I mean, you could use electronegativity or Coulomb's law to get electronegativity because your, you know, atomic radius and stuff like that.
Yeah.
But you can use it again here. But they're two completely different calculations.
The K was made to make one of those work. How do we know that the other one is in the same proportion, you know, has the same constant?
Because Coulomb's law applies to both of them.
Well, yeah, but
It is the same constant. I don't know what the proof is.
well, that's
I don't know what the mathematical proof is on that. But the constant is what makes the equation work. Without the constant, they just become meaningless numbers.
yeah. That's what I was asking was, how do we know that the constant is the same?
Because Coulomb was a smart dude. It's kind of like how you. It's kind of like talking about the gravitational attraction between a person and a planet and a planet, right? They seem to be like on completely different scales, but when you boil it right down to it, it is the same concept working just in two different scales. Like as far as quantum goes, quantum gravity doesn't use the same constant, right? But person-to-person gravity and planet-to-planet gravity does use the same constant. Cool? Is that a satisfactory answer? Okay. What? Forget the units. The units of Coulomb's constant are not that bad. The units of the gravitational constant are stupid. It's like meters, Newton, second to the -3rd or something like that. It's ridiculous. Okay.
Is that the most ridiculous constant? Or is there
Oh, I'm sure there's insane units for some
second per degrees Kelvin?
second per degrees Kelvin to the -8th. Yeah, I'm sure there's crazy constant units. Okay, questions on that? All right, so what we're going to do now in class is we're going to watch one of the daily videos from AP Chem on this. There are 2 of them. We only have time for one of them, really. If you're watching this on YouTube later, then go to the AP Classroom and watch both of the daily videos, okay? That will conclude the discussion for now.